Thank you very much for the invitation. It's great to be here, and thanks everyone for coming. So yes, this is a new project with Ilya called the Proper Scoring Rule Approach to Incentivizing Information Acquisition. And hopefully by the end of the talk, you'll be convinced that this is in fact the proper approach to model these problems with. Um, so let me start with a brief introduction. So the basic purpose of this project is to develop tools for analyzing optimal mechanism design problems for agents who acquire flexible information. And our basic motivation here is twofold. First, naturally, we're not the first to observe this. Information acquisition is a key feature in many market and mechanism design settings. For example, in organizations, managers and other experts need to be incentivized to learn about the correct course of action for the organization to take. In various marketplaces and buyer-seller relationships, buyers need to exert effort to learn about their valuations for goods before making purchase decisions. And in various prediction and financial markets, traders need to learn about the quality of assets or different investment opportunities before making their trading decisions, which are then used as signals to eventually guide the social decisions involving production and consumption. Moreover, flexible information acquisition, by which I mean the idea that agents choose not only whether to learn or how much to learn, but also can flexibly tailor what information to acquire, is increasingly relevant in the modern data and information-rich economy. On the one hand, if we think about actual production of new information, there's a whole host of new data and information sources that agents have access to. On the other hand, if we think about the costly cognitive processing of available information, agents, for example, online consumers, are inundated with more information than ever before, and therefore need to exert costly efforts to sift through it in a detailed way. And there's been much theoretical interest in flexible information acquisition in the rapidly growing literature on rational inattention, on which we'll build. So with this basic motivation in mind, the core observation of this project is that there's a duality, or in some sense an equivalence, between so-called posterior separable information costs, which are the now standard way of modeling flexible information acquisition in the literature, and on the other hand, proper scoring rules, which are familiar objects from belief elicitation tasks. We'll define this more carefully later, but a proper scoring rule is a payment rule that pays an agent based on their reported belief about the state, conditional on the ex post realized state, in a way to elicit truthful reports. So given this duality, what we show is that an agent who has posterior separable information cost and can acquire information about an uncertain state, such an agent's learning incentives are uniquely pinned down by the scoring rule that's dual to their cost function. Now, with this observation, we make a few contributions, which basically involve developing a unified approach to analyzing learning incentives in decision problems and learning incentives in a host of mechanism design problems. So our first main results, our first pair of main results, are going to be general characterizations of the optimal learning of an agent with posterior separable information costs, both in exogenously given decision problems, as well as a characterization of which learning and action strategies can be implemented via some mechanism in a rather general class of design environments that nests many applications of interest as special cases. In the sort of second third of the talk, I will discuss a series of applications of these general characterization results to a few common classes of design problems, in particular to principal expert problems, where an expert needs to be incentivized to learn and report information via state contingent transfers, to monopolistic screening problems, where a buyer needs to be incentivized to learn about their values by the design of a menu of different goods and uncontingent transfers. And then I'll briefly mention today, there's more detail on this in the paper, an application to delegation problems as well. Towards the end of the talk, I'll also discuss a series of applications to multi-agent information acquisition. I should have mentioned these three applications noted above are for single agent design problems. But this scoring rule approach also applies to multi-agent settings. And so we develop a series of applications to multi-agent settings where a number of agents are learning about a common state of nature. And what we'll see there is that there's a central role played by market scoring rules, which I'll define later. And roughly speaking, at least in one special case, first best optimal mechanisms closely resemble real-world prediction markets where the agents are compensated via market scoring rules. And throughout the project and throughout the talk, we both develop a unified approach to, in effect, rederiving some existing results from the literature, either in a more unified or more general way, as well as developing a number of new results that are new to this paper. And throughout, I'll try to highlight which results fall into either of these classes. Now, one disclaimer about the material covered in this talk. So for the vast majority of the time, I'm going to focus on the paper on which the title of the talk is based, which is mostly focused on single agent design problems. In the final few minutes of the talk, time allowing, I'll talk about results that are going to go into a companion paper, which is primarily focused on applications to many agent design problems. The title of that project is called The Costly Wisdom of Inattentive Crowds. The meaning of that title will become apparent as we go along. Okay. So this project dovetails with several strands of related literature. Let me be very brief here. I'll talk more about the most closely related papers along the way. But we build directly on a long line of literature on proper scoring rules, going back to McCarthy in the 50s and Savage in the 70s. Some of our analysis dovetails with the literature on prediction markets based on market scoring rules, initiated primarily in the computer science literature. Some of our single agent design applications are directly related to a recent line of papers focused on incentive design for a single rationally incentive agent. And then our applications to multi-agent design contribute to a much larger and longer line of literature on incentivizing multiple agents, either in simultaneous mechanisms or in various other market and social learning settings. In some sense throughout the project, but also in particular in the latter portion, we're going to be building on tools developed in the recent rational intention literature, in particular those related to single agent dynamic flexible information acquisition. Okay, so the outline of the talk is as follows. So for the first half of the talk or so, I will focus on the general characterization results, first introducing the basic approach based on proper scoring rules, and then introducing our analysis of implementation in a general class of single agent design problems. Then in the second half of the talk, we will sort of at least partially pivot from methodology into more economic applications. First, focusing on the three single agent design applications that I mentioned earlier, and then at the end, time allowing, discussing applications to multi-agent design settings. With apologies, the first half of the talk is going to be pretty nerdy. There's not going to be much market design here. It's going to be more information design. And then the second half of the talk will be a bit more concrete and focused on applications that we all care about. Okay, so first, the proper scoring rule approach. So let me begin by introducing some notation and mostly standard primitive objects. So throughout, we're going to think of there being a finite state space, capital theta, with a generic state, little theta. And we're going to think about an agent who starts with a full support prior belief, P0, over the state space. Throughout, I'll denote by delta of theta, the simplex of beliefs, and by this delta circ of theta, the relative interior of the simplex, so the set of all full support beliefs. Now, when this agent acquires information about the state, as is now standard, their information acquisition activities generate a random posterior belief, which I'll denote by p tilde, tilde denoting a random variable, which is distributed according to some distribution pi. So pi is a distribution over posterior beliefs. And by Bayes' rule, this random posterior must average back to the prior. This is the so-called Bayes plausibility constraint. Conversely, any random posterior satisfying the Bayes plausibility constraint can be generated via some information acquisition activity. So as shorthand notation, we'll call random posteriors satisfying this Bayes plausibility constraint learning strategies, and denote the set of all learning strategies by capital pi of p naught. So these are all of the random posteriors that average back to the prior. Okay. Now let me introduce the sort of two main objects, or the two main protagonists of this project. First is the class of so-called posterior separable information costs, which were defined by Kaplan, Dean, and Leahy. We will think of the agent as acquiring random posteriors, or acquiring learning strategies according to some cost function C, which just takes learning strategies into non-negative real numbers, possibly plus infinity, if some learning strategy is infeasible. And such a cost function is called posterior separable if there exists some convex potential function H defined on the belief simplex, such that the cost of a learning strategy is measured by the expected change in this potential function from its value at the prior to its value evaluated at the randomly drawn posterior belief. For those of you who are familiar with the modern rational inattention literature, you'll recognize these posterior separable costs as being the sort of now standard model of information cost in the flexible information literature. There are various foundations that one can provide for such cost functions. There's a number of axiomatic characterizations. Some of my work with Weiji Zhang, along with the work of Stephen Morris and Philip Strack and Ben Heber and Mike Woodford, have shown that these cost functions can be micro-founded as representing the reduced form cost of some optimally designed sequential learning process that's going on in the background. But for now, we're just going to take this class of cost functions as given. To fix ideas, one common example of a posterior separable cost is the mutual information cost function popularized by Sims's original rational inattention model, which corresponds to the case where this potential function H is equal to the negative of Shannon's entropy. So this is the case where H takes this particular log sum. Okay. On the other hand, the other main definition is that of a proper scoring rule due to McCarthy and Savage, and I think possibly others even earlier. So a proper scoring rule, which we'll denote by S, is a state contingent payment rule that maps reported posterior beliefs into vectors of state contingent payments such that the expected value of reporting a posterior P, given that your true posterior belief is P, is always weakly greater than reporting any other posterior Q, given that your true posterior is P. So basically, proper scoring rules are state contingent payment rules that incentivize truthful belief elicitation. For example, in experimental settings or in market settings, agents are often compensated via proper scoring rules to elicit their beliefs that the market or that the experimenter doesn't know. And let me just note, this will be important for the next slide, we can extend the definition of a proper scoring rule to any other domain in R theta, not just the simplex.
Alex, I have a quick clarifying question. Do we need
Yes.
uniform posterior separability or posterior separability? Does it matter?
Great. So uniform posterior separability means that the cost is defined via the same potential function h, no matter what the prior belief is. Whereas posterior separability implicitly means that the h function can depend on the given prior. For most of the analysis today, we're going to hold the prior belief fixed, so there's no meaningful distinction between these things. When I discuss multi-agent applications at the end, I will adopt the stronger assumption of uniform posterior separability. That will be necessary for some, but not all of the results.
Okay, thanks.
Yeah, thank you. So one canonical example of a proper scoring rule is the famous log scoring rule, I believe first introduced by Savage, where in state theta, if an agent reports that their posterior is p, they're paid the logarithm, the natural log of the reported posterior probability of state theta. Okay, so with these two definitions, our first observation is recalling in maybe slightly new form an equivalence result between convex functions and proper scoring rules. Okay. So I'm going to begin with a classical statement of this equivalence that goes back at least to McCarthy in the 1950s. I'll explain the logic of why it's true, and then explain how we apply it to our setting, where the convex functions that we're interested in are derived from these posterior separable costs. So result, a function h defined on the strictly positive orthant in R theta is convex and homogeneous of degree 1 if and only if there exists a homogeneous of degree 0 proper scoring rule, also defined on the strictly positive orthant, such that first, this convex function is defined as the value of this proper scoring rule under truthful reporting. And moreover, this proper scoring rule is a subgradient of the convex function everywhere. Okay, the proof of the only if direction is basically, can be viewed as a corollary of classical producer theory arguments. We know from producer theory that any convex HD1 function is the profit function of some competitive firm facing prices P. Here I'm just reinterpreting beliefs as prices in effect. Hotelling's lemma tells us that the supply function of this firm must be a selection from the subgradients of this profit function. Therefore, this profit function can be rationalized via the production set comprising only the supply function. And then with this analogy, profit maximization directly implies properties. Conversely, the proof of the if direction is basically immediate from the definitions. In particular, for any HD0 proper scoring rule, by construction, the associated function h, defined as the value of this proper scoring rule, is convex and homogeneous of degree. Okay. So, as I said, this is an old observation. The novelty of our analysis is going to be to apply this result to the convex potential functions corresponding to posterior separable costs. So in particular, we defined posterior separable costs via their potential functions defined on the simplex. Going forward, we're going to implicitly extend any function defined on the simplex to the entire positive orthant by homogeneity of degree 1. Therefore, we can view the potential function h in this lemma as being the HD1 extension of the potential function for some posterior separable cost. Throughout, we're going to impose some standing assumptions on this function h. In particular, we'll assume that it's finite and differentiable on the interior of the simplex, and we'll assume that it's lower semi-continuous on the whole simplex. These are convenient and mostly innocuous technical assumptions. A direct corollary of this lemma is then that for any posterior separable cost function with a potential h satisfying the standing assumptions, there exists a unique proper scoring rule, which we'll denote by S, such that S is given by the gradients of the potential function at every point in the interior of the simplex, and such that H is given by the value of the proper scoring rule for all beliefs in the interior of the simplex. And then in some corner cases, this value might actually not be attained on the boundary of the simplex, which is why this is written with a sup rather than a max. But in short, for any posterior separable cost satisfying these standing assumptions, there's a unique proper scoring rule satisfying this gradient condition and such that the potential is the value of the proper scoring rule. Now, roughly speaking, we can think of this gradient condition as saying that the proper scoring rule represents the marginal value of information under this cost function. In particular, this proper scoring rule measures the marginal cost of shifting a posterior belief by some infinitesimal amount. Okay. Now, let me explain how to apply this equivalence result to characterize an agent's optimal learning decisions in some decision problem. I should say, analyzing optimal learning in a given decision problem is a necessary warm-up to analyzing the design of mechanisms, which can then be viewed as the design of the decision problem the agent faces. So a decision problem AU is going to consist of some action set A and some state contingent utility function U that maps actions into vectors of utility consequences. In particular, if action A is taken and then state theta realizes, the agent's payoff in this decision problem is given by the theta component of this utility function evaluated at A. Now, any such decision problem induces an indirect utility of beliefs, V, defined for each possible belief as the supremal expected value that the agent could get given that belief and given that they're then choosing actions optimally given that belief. As with potential functions, we're implicitly going to extend these indirect utilities to the orthant by homogeneity of degree 1. Okay. A strategy for the agent, pi alpha, then consists of a learning strategy pi, which we defined earlier, as well as an action plan alpha, which is a rule that maps every possible belief into an action to be taken if that belief is the realized posterior. And we'll say that a strategy pi alpha is optimal for the agent if it satisfies two conditions. First, the learning strategy solves this maximization problem. So it attains the maximal value over all learning strategies where the objective function is given by the indirect utility of the decision problem minus the posterior separable information cost. Moreover, the action strategy must be such that the indirect utility is actually attained at every posterior belief in the support of the learning strategy. In other words, the specified actions under alpha must be optimal at every on-path posterior. In conjunction, modulo measure zero sets, these two requirements are equivalent to the agent maximizing their ex-ante expected utility from the decision problem. Okay. Okay. This is a good time to pause if there's any questions about definitions. Okay, great. So if not, let's dive into the characterization. Um, so it is a now standard observation that given any such optimization problem uh, over learning strategies, by concavification or associated duality arguments, in particular from the Bayesian persuasion literature, um, there must exist some vector of Lagrange multipliers, which I'll denote by zeta, um, which are the Lagrange multipliers on the Bayes plausibility constraint that posteriors have to average back to the prior, such that the support of the optimal learning strategy is contained in the subset of beliefs that maximize this Lagrangian. I'll show you a picture in a couple of slides, but this is maximizing the difference between the indirect utility of posterior P, the potential function evaluated at posterior P, and this difference is then sort of rotated by the affine function given by the multiplier dotted with the posterior. Okay. So given such a Lagrangian representation of optimal strategies, we then obtain the following characterization theorem of optimal strategies. So in particular, a strategy pi alpha such that the learning strategy is supported on full support beliefs. That is, every posterior in the support of pi has full support over the state space. Any such strategy is optimal in a decision problem AU if and only if there exists a Lagrange multiplier zeta such that for the proper scoring rule S given by the gradients of the potential function, the following two conditions hold. Condition one is an on-path first order condition that basically says that the agent is choosing optimal posteriors among those in the support and is choosing actions optimally at those posteriors. So this condition says that the vector of state contingent utilities at the chosen action or at the specified action at posterior P equals the gradient of the indirect utility at that point, which equals, in turn, the proper scoring rule evaluated at that point, plus the Lagrange multiplier zeta. And this must hold for every posterior in the support. So the way to read this condition intuitively is that the vector of state contingent utilities for every chosen action is pinned down uniquely by this proper scoring rule. Plus, we can think of this multiplier zeta as being like a side bet on the state. So this is a payoff that depends on the realized state, but not on the realized posterior. The second condition specifies that the support of the learning strategy is in fact globally optimal for the agent. And so this requires that the indirect utility must be majorized by the potential function plus the expected value of the vector zeta at every belief outside of the support. This just implies that the agent couldn't deviate to other learning strategies in a profitable way. And following the literature, we'll call this the optimal consideration set condition. Again, it just says that the support is optimal. Moreover, the ex-ante value of the agent's problem is then given by the potential evaluated at the prior plus the prior expected value of the vector zeta. Okay, so let me just briefly describe the proof sketch, and then I'll give you a picture that illustrates everything. So conditions 1 and 2 of the theorem, including the fact that the indirect utility is differentiable everywhere in the support, follows from a concavification argument that I'll illustrate on the next slide. Once we have differentiability of V on the support, the envelope theorem directly implies that the gradient must be equal to the vector of state contingent utilities at that point. Um, and then the agent's optimal value, as specified here, then follows directly from conditions 1 and 2 together with the HD1 normalization of V and H, which says that the value of the proper scoring rule must equal the potential. Okay, so let me just illustrate the theorem in a picture. So this figure is basically a standard diagram representing concavification. So here, this is illustrated in the case where there's just two states, and the x-axis here just parameterizes beliefs by the probability of being on one of the states. So the curve is the function v minus h. And what the theorem is saying is that there exists, in this case, some affine function defined by its slope zeta, such that the optimal learning strategy, or such that the support of the optimal learning strategy is contained in the set of points where this affine function is tangent to the curve v minus h. That's the on-path first-order condition. And moreover, such that this affine function lies everywhere above the curve v minus h. That's the consideration set condition. Okay. Okay, so here's the statement of the theorem again. Let me note that versions of these conditions, mostly in finite action settings, have appeared several times in the rational inattention literature. A couple notable examples cited down here. Our intended contribution of this particular result is to highlight the connection between optimal learning and the specific proper scoring rule that's dual to the agent's cost function. One other maybe smaller contribution is that this is a characterization of optimal learning for basically completely arbitrary action sets. Both of these features of the characterization are going to be important later for analyzing the design of the agent's decision problem, where we don't want to impose a priori restrictions necessarily on what the structure of the agent's action set might be. Okay, let me mention briefly. So for the remainder of the talk, I'm going to focus on applying this result to design settings. In the paper, we do consider an application of this result to characterizing the stochastic choice behavior of an agent facing an exogenously given decision problem. So in particular, given any decision problem, of interest is understanding the optimal stochastic choice rule P that tells us in every state what the agent's distribution over actions is. That's an equivalent way of describing a solution to an information acquisition problem rather than via the belief-based strategies that we're working with here. Now, it might not be entirely obvious, but from this theorem, we can back out what the optimal stochastic choice rule would be in two steps. First, you can invert this on-path first-order condition to determine what the optimal posterior would be, denoted by PA, conditional on action A having been chosen. You get this just by inverting the proper scoring rule in this way. When in the case where H is given by Shannon's entropy, and then correspondingly the proper scoring rule is the log scoring rule, this inversion procedure uses yields the multinomial logit characterization of optimal learning under mutual information costs due to Matejka-McKay and others. However, beyond this entropic case and maybe a couple of others that we highlight, inverting the scoring rule can be difficult. The second step would then be to ensure that we're at a global maximum by checking the consideration set condition. In general, this step is known to be hard. Now, let me note that in a separate paper that I have with Tommaso Denti and Luciano Pomato, which is exclusively focused on decision problems, we develop what is an equivalent but sort of dual characterization of optimal learning based on the observation that this inverted first order condition can equivalently be written as saying that the posterior at action A is equal to the gradients of the Fenchel conjugate of the potential function h, rather than of the potential function h itself. And so when you write information acquisition problems using this Fenchel conjugate h star instead of the potential h itself, you can bypass this inversion step. And when analyzing optimal stochastic choice in decision problems, this duality-based approach, at least for some purposes, can be more tractable. However, that's somewhat of an aside. For the rest of the talk, we're going to focus on applying this result to design settings, where, as we will see in a moment, both of these issues, namely inverting the scoring rule and checking the consideration set condition, oftentimes simplify dramatically or are not necessary. Okay, so next I'll move on to the general family of design problems that we consider, but let me pause here if there's any questions. Okay, great. Okay, so as promised, let me start with a relatively abstract notion of a design problem. In maybe 15 minutes, I'll then specialize to specific examples from the literature. So a design problem is going to consist of the following objects. First, there's a non-empty set Y of physically feasible outcomes. These are all the outcomes that are payoff relevant to the agent and to the principal who is designing the agent's decision problem. The agent has a state contingent Bernoulli utility over outcomes denoted by U. This is exactly the U function that I just defined in decision problems, except that now it's defined over all feasible outcomes rather than just those that the agent faces in their decision problem. We're going to imagine now that there's also a principal who designs the agent's decision problem. The principal has a state contingent Bernoulli utility over outcomes denoted by W. The agent also might have outside options. So there's two types of outside options. First, the agent has a subset Y0 of outcomes that we call quitting outcomes. These are outcomes that the principal cannot exclude from the agent, and so that the agent would be able to deviate to any quitting outcome after entering any mechanism designed by the principal and after learning any information that the agent acquires. This set of quitting outcomes could be empty. Moreover, the agent has an ex-ante reservation value, which we'll denote by U0, which could be a real number or it could be minus infinity. Minus infinity would capture no participation constraints. So the timeline that we have in mind is that the principal first designs any menu for the agent. We'll denote a menu as A. This is any subset of feasible outcomes, such that the menu contains all of the agent's quitting outcomes. This constraint captures the idea that the quitting outcomes for the agent are not excludable. These are the agent's inalienable outside options. Given the menu offered by the principal, the agent can either accept or decline. If the agent declines, the interaction stops and the agent gets the reservation value U0. I'm not going to specify what the principal's payoffs are, conditional on declination. We're just going to focus on mechanisms that incentivize participation by the agent. On the other hand, if the agent accepts the principal's menu, then the agent faces the decision problem induced by this menu and the agent's exogenously given Bernoulli utility U, and the agent then chooses an optimal strategy in the sense described previously. If the agent's indifferent, we're going to allow the principal to break ties in her favor in the tradition of weak implementation. Okay. So in the applications that I'll describe later, we will primarily think of this set of outcomes as representing physical outcomes like project choices and transfers or allocations of goods and transfers. However, of course, to any such set of physical outcomes, we can also append any message space. So this formulation encompasses any static direct revelation mechanisms. What this formalism is implicitly ruling out would be dynamic mechanisms, where the agent is asked to learn and report over multiple stages, possibly with the continuation of play in the mechanism involving randomization by the principal. At least under some assumptions, which I won't go into here, the reduction to static mechanisms is without loss of generality. But for now, you can think of this as a restriction made for tractability, and this is consistent with the vast majority of the literature. Okay. So we're going to be interested in which strategies are implementable for the principal by the design of some menu. So in particular, we will say that a strategy pi alpha, ignore the pure qualifier here. I ended up building this into the preceding slides. So a pure strategy pi alpha is implemented by menu A if the strategy is an optimal strategy for the agent when they face the induced decision problem. Again, if the agent has multiple optimal strategies, we can break ties in favor of the principal. A strategy is implementable if it can be implemented by some menu. And a strategy is individually rational if the agent's value under the strategy weakly exceeds their reservation value. It's an implication of the previous theorem that the agent's value under the strategy does not depend on the menu that's used to implement the strategy. So this is a well-defined notion. Okay. So our next main result is going to be a characterization of all implementable strategies. To state it, we will denote for every possible belief P the agent's quitting value as the function V0 of P, which is just the agent's indirect utility in the fictitious decision problem where the only available actions are their quitting outcomes. So in other words, this is the indirect utility that the agent would get if they were to ignore all of the actions made available by the principal. Okay, theorem. A strategy with interior support is implementable if and only if there exists a vector zeta such that two conditions hold. First, we have the same on-path first-order condition from the preceding theorem, which says that the agent's on-path utility is pinned down by the proper scoring rule plus the vector zeta. The second is a constraint that we call quitting rights, which says that for every belief, both those in the support of the strategy and those outside the support, the agent's quitting value must lie below the potential function plus this affine function determined by the vector zeta. Basically, this quitting rights constraint is the analog of the consideration set condition from the preceding theorem, specialized to the case where the only actions that the agent is able to deviate to are his quitting outcomes. So this quitting rights constraint captures the idea that the agent's optimal learning and that the agent's learning and decisions under the specified strategy are in fact globally optimal, given that the only actions that the agent can deviate to are those in the support of the strategy or his quitting outcomes. Moreover, the agent's value is given by the same formula as before. Sorry, this Z should be a zeta. And hence, individual rationality holds if and only if the reservation value is lower than the value under the strategy. Okay, so let me make two remarks. First on quitting rights. So this quitting rights condition resembles the standard kind of interim IR constraints that we're familiar with from mechanism design problems. In this context, the appropriate version of interim IR would correspond to quitting rights, but only applied to posteriors that are in the support of the learning strategy. Quitting rights is strictly stronger than interim IR because it applies to all posteriors. And this is capturing the idea that the agent can deviate not only by opting out of the mechanism and taking a quitting outcome after following the specified learning strategy, but the agent can also follow double deviations where they first use a different learning strategy and then deviate after those off-path posteriors. A second remark is that this design problem, the theorem tells us that the design problem is simpler than the decision problem in two respects. First, for most purposes, we can work directly with this first order condition and the quitting rights constraint. We don't actually need to invert the scoring rule. And second, because the principal can always, without loss, implement a strategy by excluding all of the outcomes other than those that are used on path in the strategy and the agent's quitting outcomes. So because the agent can shrink the agent's menu basically at will, subject to this restriction, the quitting rights constraints is oftentimes much easier to check than the consideration set condition. So let me note that there's two limiting cases that might clarify this. First, if the agent set of quitting outcomes equals the set Y of all feasible outcomes, this quitting rights constraint exactly reduces to the consideration set condition from the previous theorem. On the other hand, if the agent does not have any quitting outcomes, so the set Y0 is empty, the quitting rights constraint goes away, and the principal can just optimize directly subject to this first order condition. Okay. So the main implication of this theorem is that it reduces the principal's a priori very high dimensional problem of designing a menu, which might in applications consist of designing high dimensional state contingent transfers and arbitrary allocations of goods or projects. It reduces the design problem down to the principal's choice of choosing a strategy and a vector zeta subject to these two constraints, which are relatively easy to work with. So let me illustrate the theorem in a picture. Here again, we're specializing to the two-state case where the x-axis parameterizes the probability of, say, state one. This convex blue curve is the potential function plus, shifted by the affine function given by the vector zeta. And let's suppose that the strategy to be implemented has binary support. So there's two posteriors, P lower bar and P upper bar, and two corresponding actions. So the on-path first order condition specifies that the agent's expected value for the on-path action at posterior P upper bar is tangent to the blue curve at P upper bar and otherwise lies everywhere below. And similarly, the agent's action or the specified action at posterior P lower bar, the expected value of that action is tangent to the curve at P lower bar and otherwise lies everywhere below. The quitting rights constraint is then represented in the figure by the fact that the agent's quitting value, here I'm considering a setting where the agent only has a single quitting outcome. So this quitting value is just an affine function. So the agent's quitting value at every posterior must lie below the blue curve. Here it lies strictly below. Moreover, in this figure, individual rationality is satisfied because the agent's reservation value lies below the height of the blue curve evaluated at the prior, which is the agent's optimal value under this strategy. Okay. So I think I'm going a bit slow, so let me try to speed up a bit. One immediate implication of this result is that in settings where the agent only has a single quitting outcome, and where there's sufficiently transferable utility between the principal and the agent, such that at the optimum, the quitting rights constraint must bind somewhere. These are both standard features of most mechanism design and contract theory models. In such settings, the side bet vector zeta is actually uniquely pinned down by the belief at which the quitting constraint binds. So in particular, suppose the agent only has a single quitting outcome y0, then a pure strategy pi alpha with interior support is implementable and satisfies the quitting rights constraint with equality at some interior belief p hat, if and only if the agent's on-path state contingent utility is given by the scoring rule evaluated at the posterior minus the scoring rule evaluated at this critical belief where the quitting rights constraint binds, plus the utility that the agent would get under their quitting outcome. Okay, so in such settings, we can actually dispense with the quitting rights constraint. And the principal's choice of the vector zeta is uniquely pinned down by any beliefs at which the quitting rights constraint binds. In applications, this makes the design problem quite tractable. Okay, so going back to the same figure, if the quitting rights constraint binds at some belief p hat, meaning that in, the agent's quitting value is tangent to this blue curve at p hat, the tangency condition implied by this delivers this specific first order condition. Okay. Now let me immediately use this result to obtain a result that might be of economic interest. So in many of these same settings where the agent has a single quitting outcome and there's transferable utility, or at least some degree of transferable utility, it is often the case that obtaining the principal's first best payoff, for example, the principal's maximal profit, given that they could control what the agent does, requires the agent's ex ante IR constraints to bind. In such settings, we can uniquely pin down what the agent's payoffs must be under any implementable strategy. So in particular, suppose there's a single quitting outcome, and suppose that the agent's reservation value is given by the prior expected value of this quitting outcome. And this is a mostly standard normalization in applications. Then a pure strategy with interior support is implementable and satisfies the ex ante IR constraint with equality if and only if the agent's state contingent payoff at every on-path posterior is given by this object, which is called a market scoring rule. That is the difference between the scoring rule at the posterior and the scoring rule at the prior, plus the utility of the agent's unique quitting outcome. So let me just first illustrate this in a picture and then discuss. So the theorem follows immediately from the preceding proposition once we realize that given the normalization that the agent's reservation utility equals the prior expected value of the quitting outcome, ex ante IR holds with equality if and only if the quitting rights constraint holds with equality at the prior. And then that means that we must have this tangency condition from the preceding result at the prior, and that uniquely pins down, or semi-uniquely pins down p hat to be the prior. Okay, so what is this result telling us? Well, market scoring rules of this form, where an agent is compensated according to some proper scoring rule based on the difference in the scoring rule at the prior and the posterior, are used, for example, in many real-world prediction markets to elicit truthful reports from agents who have exogenously given private information via state contingent monetary payments. So in a standard prediction market setting, an agent might be paid a monetary amount with this functional form. In other words, a market scoring rule is a particular kind of state contingent security. What this theorem is telling us is that at least under some conditions, under some conditions on the environment where first best optimality requires a binding ex ante IR constraint, these market scoring rule payoffs for the agent are uniquely optimal not only for eliciting truthful reports from the agent, but also for incentivizing the agent to acquire the appropriate information. And this is true even if these payoffs are delivered via non-monetary instruments like the allocations of goods or projects, and or the outcomes are non-contingent, so they don't involve state contingent transfers. So in sum, this is telling us that market scoring rules, denominated in utility terms, are under some conditions uniquely optimal first best mechanisms for incentivizing information acquisition. Okay. So this concludes the first portion, the sort of abstract theory portion of the project. I see that I didn't manage my time very well, so let me at least quickly outline what we do in the applications, which maybe are the more exciting part. In this, we consider 3 single agent applications. The first is a principal expert problem, where the principal where the agent is an expert who only cares about money, and the principal wants to incentivize the agent to acquire and report information truthfully to guide the principal's choice of project that yields some state contingent returns. And in this model, the agent can be incentivized with state contingent payments. Our main result is that, building on the previous market scoring rule theorem, is that the principals the principal can implement their first best optimal strategy if and only if they pay the agent using state contingent payments that take that market scoring rule form, and the agent is risk neutral. In particular, if the agent is strictly risk averse, you can't attain the first best. And an implication of the market scoring rule representation is that even if the agent is risk neutral, you typically can't attain the first best if there are limited liability constraints. But at least if the agent has access to quitting rights, market scoring rules are the uniquely optimal first best mechanisms in this setting. The second application is to a setting of monopolistic screening, where the agent is a buyer who needs to be incentivized to learn about their values for goods before making a purchase decision. And the main result there is that under some generic conditions, the allocation is distorted at every posterior in the support of the optimal learning strategy. So in particular, there's distortion even at the top, in contrast to standard mechanism design with exogenous information. And the result here basically generalizes some prior results of Mention, Ravid, and Therese to settings where there's possibly multiple goods and a broader class of cost functions. Our final application to delegation considers delegation problems where the agent and principal have aligned interests in the sense that their utility functions are the same, but the principal doesn't directly internalize the agent's information acquisition effort. So there's an effort under provision problem. In this context, the agent is we can think of the agent as being a subordinate to the principal as a manager. And the only instrument that the principal has available is restricting the agent's action set. There's no transfers allowed. And the main result here is that at least when the state is binary, at least when the state is binary, the optimal delegation set includes only extreme actions. That is, actions that would be optimal at relatively low posteriors, or actions that would be optimal at relatively high posteriors. The only way that standard interval delegation sets could be optimal is if actually delegating the full action set to the agent is optimal. So in other words, whenever there's value to the principal restricting the agent's action set, The optimal way to do that is by excluding intermediate actions that are optimal at intermediate or sort of safe posteriors. And this application does not directly rely on the market scoring rule characterization that I just gave you, but it illustrates how the framework can be used in settings without transfers, quitting rights, or even IR constraints. So unfortunately, for the sake of time, I'm going to skip over these applications. Let me just quickly mention what we do in the multi-agent setting. So everything so far has been about single agent design problems, which are of course standard in many contract theory type applications. Naturally, though, many design problems with information acquisition involve multiple agents. Think about a team of agents learning about some common state. For example, traders learning about the state of an underlying technology in a financial market or prediction market, or a group of agents learning about their own private values as in options. In such settings, optimal mechanisms are often dynamic, with agents learning and reporting sequentially one after another. And it can often be useful to harness the wisdom of the crowd by hiring a large number of agents so that you can spread the work of acquiring information among multiple agents, and also make each agent's private information small. It turns out that this proper scoring rule approach can be applied to these other more complicated settings. So in a multi-agent application contained in this paper, we show that in basically a multi-agent extension of the principal expert application, when the agents are risk neutral and learn about a common state and can be incentivized via state contingent transfers, MSR, or market scoring rule mechanisms, in which agents move sequentially one after another and are compensated with these kinds of market scoring rule payments, are the essentially unique first best optimal mechanisms. This is true even when the agents are capacity constrained in terms of how much they can learn, which provides a motive for spreading the work among agents, and even when the agents are subject to limited liability constraints. So the optimal mechanisms in this setting reasonably closely resemble real-world prediction markets where agents do move sequentially and trade market scoring rule securities with an automated market maker, and therefore it can be viewed as a kind of optimality foundation for these kinds of prediction markets. In the companion paper that I mentioned at the beginning, we consider a richer setting where the agents are risk averse and are still learning about a common state. And our main result there is that when the agents are strictly risk averse, no mechanism can approximate the principal's first best cost, even as the number of agents goes to infinity. So we think of this as being a kind of fundamental impossibility result, indicating that there is an intrinsic tension between informational efficiency in the sense of incentivizing the agents to acquire and report the requisite information, and allocative efficiency in the sense of full risk sharing among the agents. And so this impossibility result applies to many settings, or to many contexts, like financial markets, where there's a dual concern for both risk sharing and for generating information acquisition that can be then used to guide social consumption or production decisions. So, with apologies for having to skip the details, let me just conclude. So this project observes that there's a duality between posterior separable information costs and proper scoring rules. Using this observation, we develop a unified approach to analyzing optimal learning in both decision and design problems with flexible information acquisition. The analysis highlights the central role of scoring rules, and in particular market scoring rules, for implementing optimal mechanisms and for achieving first best efficiency. As mentioned, in an application to principal expert problems, market scoring rule payments uniquely implement the first best. In an application to monopolistic screening, market scoring rules typically don't implement the first best, and whenever the first best is not attainable, there's distortions at every posterior in the support of the second best mechanism. And in multi-agent settings, prediction market-like mechanisms in which agents are compensated with market scoring rules are first best optimal under risk neutrality. and there are intrinsic tensions between risk sharing and optimal incentive provision in settings where the agents are risk averse. A final takeaway message is that at least for us, this perspective based on proper scoring rules has has the potential to unify and simplify the analysis of a lot of these kinds of design problems with flexible information acquisition. In this project, we've considered a handful of applications that are of interest to us and to the literature. But of course, there's many open questions remaining and many possible applications to be considered in future work using this approach. So with that, thank you for your attention, and I'll